Now, in the mass spec introduction video, I mentioned that there are some ionization sources that take the inlet into the instrument and merge it with the ionization. So we're doing conversion into the gas phase and ionization at the same time. Electrospray ionization, or ESI, is one of those types of ionization. So when you're doing ESI-MS, this is really easy to interface with a liquid chromatography method, because we can take liquids and not only get them into the gas phase, but also get our analytes ionized as well. So how does this work? Okay, let's sketch an electrospray ionization source. So we're going to start our electrospray ionization source by obviously introducing our liquid. And we're going to do this through a metal capillary. I'm just going to draw it as two sides. They look kind of like plates, but this would be a circular, very thin tube, right? Capillaries are very, very narrow in diameter. And the reason I want this to be a metal capillary is because I want to be able to put a charge on it. Okay, so we've got this kind of metal capillary here, and we're going to apply a charge. Apply a charge to it. And we're going to do this by kind of connecting it to some kind of a applied voltage. I'm just going to draw my little applied voltage here. And we're going to have to, connect a circuit. So I'm just going to draw some little plates over here that will connect it to. This might be like a ring anode. And we're going to do this so that we have the electrons flowing from the metal capillary into our end kind of focusing ions. Okay. All right. So what happens when we put a charge on a metal capillary with a solution that contains some kind of salts? Okay. We've got our liquid coming in here, and my liquid might contain our analyte, which I'm again going to write as the M, and we might have some dissolved salts. So we've got kind of positive charges and negative charges in there, in this liquid. So as we apply the voltage, we get the liquid coming out, and instead of coming out in droplets or kind of rounded as we would expect from the surface tension, we get them coming out in this cone shape. So the liquid kind of pushes its way out into what we call a Taylor cone until we get a droplet. Here's my droplet. And in that droplet, I not only have my analyte, my M, and I might have more than one of those, but I also have a handful of these little salts. And I'm going to focus on the positive ions, though there are also negative ions as well. We're going to focus more on the positive ions here. All right, so we have this droplet. It's now a droplet in the gas phase, and what happens to a droplet in gas phase? Well, we're going to start evaporating off the solvent, right? The droplet's going to start drying, and as it evaporates, it's going to shrink. Now it's smaller, okay? But in that droplet, we still have my molecules, and now we have still the same charges. I think I have 7 drawn there. Now these droplets, or these charges, are going to be as far away from each other as possible, and I've drawn them kind of along the outside of the edge. I know it's a little bit hard to see at this scale, but these droplets, or these charges, are going to try to be as far apart from each other as possible, so they're going to kind of rely on the surface. But at some point we have evaporated enough that there is no longer enough elbow room. The social distancing is not happening there. They're fed up with each other, and they're going to have such repulsive power between those like charges that they're going to break apart the surface tension of the droplet and break the droplet into multiple smaller droplets. Okay. So now in one droplet I might have 2 of the M's, in another droplet I might have 1 of the M's, and let's say we have kind of 4 of the charges moved with that one and 3 of the charges stay right here. Okay. Now we're going to continue this process of removing solvent. As it starts to dry, the droplet gets smaller, it explodes again. We're going to do this over and over, and sometimes you're going to get droplets that don't have any charges, and sometimes you're going to get droplets that still have charges. So for instance, if this one explodes, one's going to have an M, the other one won't. We might put one of our molecules in each of those. We might have one of our pluses, we might have 2 pluses still there. I'm just kind of adding these charges. And we're going to keep doing this process until there is no more solvent left. Okay, it keeps exploding or drying and then exploding, drying and then exploding until there's actually no more solvent left. Okay, and at the end of the day, you're going to have your little molecules, and they can have several different charges, right? So we've got little charges here attached to them. Now all of these charged molecules are going to again be drawn through this slightly negative, because the electrons have kind of congregated there based on our applied voltage, and they're going to be pulled through down to the mass analyzer. Okay, so at the end of the day, we have our ions that have been coordinated with salts, those cations from the salt, and that's where those positive charges are coming from. We aren't adding electrons or losing electrons. We're adding a cation here where they're positively charged from that salt. So the ions that we make are all adducts. Just like we said with the chemical ionization, if our positively charged ion in the salt is a hydrogen, because we're using a very acidic solution, we have an M plus H. But we can also do things like using sodium, we can use potassium, we could even use something like an ammonium ion. Okay. And in each of these cases, remember that when you're talking about a mass to charge ratio, the mass is going to be whatever your mass is from the molecule plus the mass of your adduct. So here you might have a mass of your molecule plus 1, because hydrogen has a nominal mass of 1. For your sodium, you might look at M plus 23. Potassium, you're looking at M plus 39. And here you're looking at M plus 18. So the mass that you would expect to see your molecule at when you're using electrospray ionization is not at the molecule's mass, but is at the mass of the molecule plus the adducts. Now all of these are positive ions, and so we can say we would do this in positive ion mode, where our charges here have the electrons being drawn away from the metal capillary, and so we get these positive ions. However, we could do this in what we call negative ion mode, where we kind of reverse this, where we have a positive here, we've got the electrons being pulled away from those focusing plates and being deposited onto our metal capillary tube, and the process would be reversed here, where I've drawn the positive charges here, we'd have negative charges coming in. And so we can get our coordination of our M plus a negative ion, such as a HCO2, or perhaps CH3CO2. Okay, so those are your kind of carbonates. Or we could even perhaps lose a hydrogen. That's also a possibility. And so in this case, you'd be looking at masses that again either add the adduct, or rather than coordinating with a hydroxide group, it's more likely that you would have a loss of a hydrogen. So in these cases, these would be considered that negative ion mode. And depending on the structure of your molecule, it might be more favorable to do negative ion mode instead of positive ion mode. Now, no matter which mode you're doing, if your molecule is particularly large, you could get multiply charged adducts. So if the molecule is large, you get multiple charges. So in this case, if you have multiple charges that are all, or multiple adducts that are all hydrogen, you get a number of hydrogens and N plus. And so your mass to charge ratio here is going to be your mass plus NH, mass, right, divided by the number of charges. So if you have something that is, has 20 hydrogens on it, you have to take the mass of your molecule, add the mass of 20 hydrogens, and then divide that by 20, and that's going to be where you're going to look for your mass to charge ratio when you're doing electrospray. Okay, we can also have, many more sodiums. We can have many, capital M, NH for many ammonium ions. So those are all examples of ways that we could do multiply charged. In all of these cases, electrospray is a soft ionization source. We're making these adducts. We are not fragmenting. So much like CI was soft ionization, so is ESI. These are both soft ionization sources. Some of the other types of soft ionization sources out there, while we aren't going to cover them in videos, you can read more about them in your textbook, would be matrix-assisted laser desorption ionization, or MALDI. And MALDI was actually introduced around the same time as electrospray, and the inventors of MALDI and electrospray actually share a Nobel Prize for this work because electrospray and MALDI both opened up the opportunity to use very large molecules for mass spectrometry analysis. Another soft ionization is atmospheric pressure chemical ionization, which is similar to our traditional chemical ionization, but instead of only having methane, we're actually doing our introduction at atmospheric pressure. One of the hard ionization sources that we aren't going to get to talk too much about is direct analysis in real time, or DART analysis, but that would also fall under hard ionization. And you can read more about that one as well in your textbook. But the three main ones that I want you to know about are electron ionization, chemical ionization, and electrospray ionization.